So, good morning, everyone, and welcome to this first session on the doctoral meetings. Sorry, there's a mistake here. In this track, we're going to be hearing about 4 PhD students working on computational and experimental aerodynamics. And they are Yunwei Chen, who will be talking about his thesis on data-driven flow measurements. Exan Farzamnik, who will be talking about statistical learning tools for turbulent flow control. Jacopo Tirelli, who will be talking about his thesis on data-driven enhancement of optical measurement techniques. So 3 theses on experimental fluid dynamics, mixing data-driven techniques, and trying to characterize flows. So very interesting talks. And then Juanma Catalan, who will be talking about his thesis on unsteady aerodynamics of flapping wing micro air vehicles. This is a more numerical aerodynamics thesis. So thanks very much for being here. And now,
I'm Ehsan Farzamnik, first year student in PhD program in Aerospace. My title is Statistical Learning Tools for Turbulent Flow Control, which is supported jointly by Comunidad de Madrid and our university. I'm doing my thesis under the supervision of Dr. Andra Yaniro from our department, and also Dr. Vanessa Guerrero from Department of Statistics. And I had the opportunity to be in contact with some other professors from our department, especially Dr. Stefano Dicetti and also Dr. Bernouak from Harbin Institute of Technology in China. So let's start with our motivation toward our thesis title. Well, turbulence is a regime of flows that literally we can say that we could see the turbulent flow in every day of our life, from day-to-day applications in, for example, water, dealing with water and looking at clouds, to let's say outer space in other let's say galaxies. For example, we also see the turbulence there. And also this turbulence and studying turbulence has a lot application in designing our system, for example, in designing of airplane and in designing of pipelines, in forecasting, for example, the weather. We used to study the turbulence. But despite the fact that there are lots of application of turbulence flow, the reality is that the knowledge of turbulence, the knowledge of physics of turbulence is still limited. And it is said that the turbulence is the oldest unsolved problem in physics. And also, on the other hand, we have flow control. In some cases, we want to decrease or increase some features, some phenomena in flows, and to do so, we need a, let's say, control system and an actuator to do this. But before designing a control system, we need to understand the flow much better, you know. And one thing, let's say, discipline that helps us a lot is the statistical learning, using the statistical methods that are quite fashion in these years to study the flows, to study this complex flow, and use it to actually design a control system in our applications. So if we want to talk about the literature regarding these topics. I want to mention the topics about the dimensionality reduction methods. In this work, we use isometric mapping or Isomap, and which was developed in year 2000 by Tenenbaum. And I will explain the dimensionality reduction methods later. But if I want to say a quick and short sentences, is that we have a lot of data, and we can say that this data lies in a high dimensional space, and we are going to construct let's say more meaningful space in low dimensional space, and to do so we use these methods. For studying the turbulence, there were lots of different approaches, especially in designing of control systems. For example, some let's say some groups started to use Galerkian model to use the spatial modes, first modes of the flow, to construct a baseline for control system. Also, there are some people using learning. And if we are going to talk about implementation of the dimensionality reduction method into the analysis of the turbulent flow, we can have that there are some research, but actually the literature in these topics is really sparse. So we want to focus on this field, implementing the dimensionality reduction method to study the turbulent flow, to construct a baseline for the designing of the control systems. So we define our objectives as follows. At the first, can we, let's say, find meaningful low dimensional structure hidden in the high dimensional experimental or simulation observations? And can we relate this low dimensional space coordinate to, let's say, some physical characteristics of the flow, which we are interested to study to construct the flow control system? And at the end, can we use this low dimensional space to construct a, let's say, design a control system? The first two topics are those that we focused on this year and in this presentation. So I'm going to give a brief summary about our methodology and also some, let's say, preliminary results. To have a, let's say, big picture about our method, from here, from, let's say, input, we have some experimental data, we have maybe some simulation. It could be anything, not like, you know, the flow visualization or something like this. It could be any application inside the, for example, the space application, inside the structural design of aerospace things. So in general, we have some snapshots of our, let's say, experiment. And from this data, we have an encoder part, which is the dimensionality reduction method. In this case, we use Isomap. I will explain the steps of this Isomap. And on the other hand, so from snapshots, or in other words, from our high dimensional space, we use an encoder to construct a low dimensional space which has, let's say, more meaningful data in this low-dimensional space. And on the other side, by using this low-dimensional space, we develop a decoder based on the KNN method to reconstruct or high-dimensional space, or let's say, snapshots. So if you want to have a very brief glimpse of these techniques, we can say that in high-dimensional space, for example, here we have 3 dimensions. It is good to visualize. And in this space, we clearly see that there is a manifold that our data lies on. So if we are able to wrap up this manifold and understand it better, we can have, let's say, low-dimensional space in 2 or 3 dimensions, which provide us a very good playground to study our data set. So for those who are familiar with this method, the Isomap is a nonlinear method in comparison with the linear one like PCA or POD in our case, or MDS, multidimensional scaling. And if we are going to talk about the steps that we do follow to implement Isomap, at the first step, we construct a neighborhood graph based on selected K. And after constructing this neighborhood graph, we compute the shortest path between any 2 points inside our data set in high-dimensional space. And by using these graphs, we are able to construct a low-dimensional space. For example, from 100,000 of dimension, we can construct a 2 or 3 dimensional space, which maybe provide us a good manifold. And on the other hand, by using the low-dimensional space, we can again use k-nearest neighbors to construct another graphs, and estimating the gradient tensor by using these neighbors to reconstruct the flow field. So let's move to our preliminary result. We have 3 different data sets. One of them is the simulation on this fluid pinball configuration, and also 2 other experimental data sets. Today I just focus on this pinball configuration, and because it is a very interesting thing. It is really complex. From low Reynolds to high Reynolds, it encounter different regimes, from steady symmetry to very chaotic things. So what are our expectations from this method? The first one, and one of the interesting things, is that is the true dimensionality of our data set. So, for example, in this special case, in high dimensional space, we had something like 1,500,000 dimensions, which are our pixels inside inside the snapshot. And from 1,500,000 dimension, we decrease the dimension to 10, 9, to 3, to 1. Okay. This graphs shows, let's say somehow the error that we can have in each low dimensional space. And as you can see, in 3 dimensions, compared to the other higher dimension, we still have a low error, or better say, explain residual variance. And after it, our error increased rapidly. So we can say that the best place, the best dimension that we can reduce our dimensions is three. So we can say that we are able to find a really interesting manifold and visualize it inside a 3-dimension from, let's say, a high dimensional 1,000 dimensions. So, for example, here, we are able to see some interesting flow features in just a really nice manifold in 3 dimensions. For example, in this case, from bottom to top of this manifold, we can see the transition between from the steady solution to, let's say, unsteady limit cycle to a steady limit cycle, which correlate perfectly with other literature on studying this flow configuration. And we are able to find this transition, this flow features without using any, let's say, physical formula, without using any Navier-Stokes equation, and just by doing some data analysis. And it is really interesting. For example, you can do it in your cases, and it has it could have some interesting results. And not only we are able to find a meaningful and interpretable manifold in low-dimensional space, we also find some interesting relation between our coordinates in low-dimensional space with the most interesting force coefficient of our flow, for example, CD and CL. So these are very quick summary of our work in this year. And after it, we are going to focus on our third objective in designing a control system for this flow regime. And maybe we are considering it to construct and realize an experiment to study the performance of our control system developed by using this method. Once more, I would like to thank Comunidad de Madrid and our university to provide me the opportunity to do this work. And thank you for your attention. I'm here to hear about your question. And if you want to have more information, you can text me or send email to this email. And yeah, that's all.